Thank you, Kevin. Yes, precisely one of the things I want to do is just share some of the things I'm thinking with you. I visited here in February because I was giving a seminar in Stanford, and I just popped over to meet some of you guys, and I noticed that this is a very interdisciplinary crowd, and some of the things I've been thinking about veer dangerously into other disciplines, and I want to explore the possibility of developing these ideas further when I'm here in the spring. So one of my goals would be to gauge the crowd and see who might be interested in these reflections. And I'm going to skip introductions about who I am or what, the About Me page, and invite you to visit our website where there's a splattering of samples of things that we do in teaching and research, mixed with some tweets and little few and far between blog articles, and get right to it. This conversation today is an extension of what I already started talking about at my keynote last year at SciPy. The title of the talk was, "If there's computational thinking, there's computational learning." It was a keynote at SciPy. Last year, the conference had a specialized track on education, so I was able to take advantage of that, focus on that topic, because I had just finished an interesting experience teaching a course on aerodynamics using IPython, now Jupyter, notebooks, and more about that later. And for some reason, I connected with the buzz over the idea of computational thinking. And then I started developing this idea that computing generates new knowledge. I'm a computational scientist, and you know that you use computing through simulations or data analysis to create new claims to scientific knowledge. And this is why we care about reproducibility, another of the topics that is a focus area in here at BIDS. And so this got me thinking that indeed we could translate that idea from our research activity to teaching and learning, and perhaps develop some narrative about what the role of computing can be in pedagogy, in teaching. And so let me trace you back through this sort of path that I took and tell you a little bit about this idea of computational thinking. In 2006, as you can see here, Janet Wing, then a computer science professor at Carnegie Mellon, now she's VP of Research at Microsoft, and she had a stint as a division director at NSF. She published a short viewpoint paper on the communications of the ACM titled Computational Thinking. And this kind of brought to the forefront of the computer science community this series of conversations about computational thinking. Janet Wing, between the years of 2001 and 2007, was at NSF, and she led huge investments in cyber infrastructure. And she used this narrative of computational thinking to get a lot of people interested and extend the investments of the NSF in computational science. She went on a speaking tour and did lots of talks all over the United States with this topic of computational thinking, in which she talked about an attitude, a skill set that everyone can use, not only computational scientists. She also says that computation can be added to reading, writing, and arithmetic as a fundamental skill that we could even start early to try to get children involved in developing. But then she proposes that computational thinking involves solving problems, decomposing problems in a certain way, trying to approach problems in all sorts of applications with fundamental ideas from computer science like decomposition, abstraction, recursion, and things like that. So ideas that are basic to computer science, she said, can be applied to solving problems in any other field. And in her speaking tour, she often used the example of computational biology as one subject where computing has had a big impact. And another example that she often uses the field, the subject of machine learning as one area of computing that has impacted our lives in many applications, e-commerce and all sorts of things that are part of our daily life, where machine learning has now basically changed the way we interact with entertainment and reading and shopping and so on. So that's the story behind this publication. And as you can see here, a few days ago, I searched on Google Scholar, and this little 2-3-page viewpoint paper with no references and no real scholarly content has 1,654, or probably has more now, citations according to Google Scholar in 9 years. Now, I don't know about you, but I would be thrilled if one of my papers got this amount of citations, even in a decade. And so it's, well, in engineering, the number of citations, perhaps in biology or computational biology, the number of citations are in those numbers. But in engineering, it's not that often. I don't know about computer science, but it seems like a pretty respectable number of citations. Now, the phrase computational thinking, nevertheless, goes back all the way to 1980. It was first used by Seymour Papert, and I've taken a screenshot there from Google Books or something of the page 182 of the book Mindstorms by Seymour Papert in 1980, where he uses that phrase for the first time. And it also appears more, treated a little bit more extensively in this paper, An Exploration in the Space of Mathematics Education, an extra S, I think, there, in 1996. Wing doesn't mention Seymour Papert, and I guess a viewpoint article or essay doesn't really need to have citations, but I find it important to go back to the source and understand, and I found it very useful to go back to the source and read those original mentions of the idea, because it turns out that it's a lot richer than how the idea of computational thinking has been popularized since the Viewpoint article in 2006. And we'll get to that. All right, now we even have a Google MOOC, Massive Open Online Course, for those that have been under a rock, that is being offered, of course, free of charge through the new course platform of Google. And this is aimed at educators with the idea that they could adopt computational thinking as something that can be used in the classroom. And in Google's version of the idea of computational thinking, I'm going to give you what this course describes as the key of computational thinking. These are the key features according to this course in Google. And you can also draw, these terms are also used by Jeanette Wing in her Viewpoint. The idea of using decomposition, breaking down a problem into simpler parts, pattern recognition, observing patterns and irregularities in your data, abstraction, identifying the general principles that unify the patterns you noticed, and algorithm design, devising a process for solving your problem. Now, you notice that the focus now is completely on problem solving, and that's how it is viewed popularly, more in the popular version of computational thinking, the idea that you can have a skill set to approach problems. Now, Seymour Papert, here's a picture of Seymour Papert. How many of you guys know or have heard of Seymour Papert? All right, maybe half the room or less, 1/3 of the room. He was one of the pioneers in artificial intelligence, a professor at MIT way back when, and also the inventor of the Logo programming language. So many of you have perhaps interacted with Logo or remember about the turtles. How many of you guys know about Logo and the turtles? More? Okay. Well, that's a turtle. That thing that you see in that picture is a turtle, the original turtles. Now, perhaps some of you computer science students or those who were exposed to computer science in school may have seen a little blip on a green screen and called that a turtle. But the original turtles were physical little toys, robots that were used by children to draw pictures on big pieces of paper on the floor. And Seymour Papert's meaning of the idea of computational thinking was deeper than the now popular version, the buzzword. He said, "My interest is in universal issues of how people think and how they learn to think." So it's not just problem solving. There's a little bit more subtlety there. And that's what got me really interested because of the experience that I had in the classroom using IPython notebooks. They were called IPython notebooks then. I'll switch to Jupyter when we move to the future in my story. And what I had experienced in the classroom using this approach to teaching aerodynamics, I was really moved by this deeper meaning of computational thinking that we find in the original writings of Seymour Papert. And I had a little 2-minute video, 1972 video, that was an optional. The technology doesn't let me show you the video right now because I don't have audio, but I can show it to you at the end once they finish the recording of the official part of the talk. And I think you will enjoy that. And here is another little bit from the book Mindstorms. He's talking about the visions that people have about using computers previously in this passage and saying all of the ways that people talk about using computers. And then at the end of the previous paragraph, he says a few talked about the computer as a teaching machine. A few, like really nobody's thinking about that, was the tone of that passage. This book poses the question of what will be done with personal computers, but in a very different way. I shall be talking about how computers may affect the way people think and learn. I begin to characterize my perspective by noting a distinction between two ways computers might enhance thinking and change patterns of access to knowledge. If you think about this, it really is, he's thinking deeper than just the idea of using computational thinking for problem solving. And I'll switch gears now and tell you a little bit about my path using Python in teaching and then connect back with this, okay? So in my TyPy talk last year, I simply said, these Jupyter notebooks are a killer app for education, and I really think that if they are incorporated in the teaching of technical subjects and mathematics, we can really do something transformative. And I want to tell you a little bit how I got to that conviction. I will share some of my experiences. The background for this was that back in 2011, I was writing or preparing to write my NSF career proposal. And my teaching methods at the time were pretty much standard. I would lecture, as I am right now, making the best effort to keep people awake, but nevertheless, it was a one-way transfer of information type of model for teaching. And so I knew that there was a need for looking to increase the level of interaction with my students, and I started just researching online for ideas on how to do that. And I bumped into this concept of the flipped classroom. And this is 2011, and I want to show you this trends notebook, this trends plot of on Google of the term flipped classroom. And I think that I probably was one of those 5 people that searched for the term in May 2011 as I was preparing for my NSF career proposal, because I submitted in July 2011. Now, of course, the term now takes off and becomes a buzzword, and now, January 2015, at the beginning of this year, like everybody had to do flipped classroom, and it becomes this thing that you're starting to feel a little bit suspicious about because it's all over the higher ed media, right? Unfortunate, but because that produces a backlash. But it was for me really transformative to think about a flipped classroom, or this basic idea whereby you understand that just being exposed for some new information for the first time is really the easy part of learning. The harder part of learning is when you have to assimilate that new concept or idea and apply it on something new. And the idea of the flipped classroom is, of course, you move that easy part of being exposed to a new concept or content for the first time to outside the classroom, when the student can read, not necessarily watch videos, read or in any way prepare to come to a very active classroom where you apply inquiry-based learning or any form of active learning to assimilate and apply knowledge in a group setting collaboratively with peers and the instructor. That's the general idea. Unfortunately, in this flat line where it becomes a buzzword, the general opinion of flipped classroom has been that you record video lectures. So it's a very shallow sort of view of that. The important part of flipped classroom, of course, is what you do in the classroom, not how you manage to transfer information. Content is the easy part in this digital age, right? How you deliver content, there's a million ways. There's the internet. You don't even have to package it very much. Okay, so this is the background, and I was teaching at Boston University a class in computational fluid dynamics at the time, and I decided to flip the classroom. And I had a track record of using technology in my classroom, and I was recording my lectures through screencasts. That is, I would do annotations on a graphic tablet while I was presenting, and then record that and put it online so that the students would be able to revisit the material, because I knew that half the people were falling asleep in lectures because lectures are passive. Now I don't do that anymore. Anyway, I had some videos, and so I was able to, I had that initial, I removed that initial friction of not having to record videos because I already had them. And I used the videos from the previous year and decided just to, in 2012, to develop something active to do in the classroom. And we used, for the first time, Python. And not in that version of the on-campus class, but afterwards, I had to teach a summer school. And I just grabbed this exercise that I had developed for the classroom that's called the 12 Steps to Navier-Stokes, and it's literally 12 steps for coming at the end of it to write your own version of a Navier-Stokes solver in 2 dimensions with Python. The first step is the easiest possible PDE solver that you can imagine, which is this find a different solution of a 1-dimensional linear convection equation. So it's the easiest partial differential equation that you can write down. And from then, slowly adding elements, at the end of 12 steps, you actually have a Navier-Stokes solver. And that had worked well in the classroom, but my students in the classroom took normally about 5 weeks to complete that. And then, with the help of my able PhD student, we developed this as a set of notebooks and published this. This is, of course, available for everyone to use under an open license on GitHub. And I used it on an intensive summer school in Argentina when I had 2 days to teach numerical CFD, to teach numerical fluid mechanics. And I found I had 20 students, quite a diverse group, some physicists, some students that were programmers, some others that didn't really know the program very much, and it's quite a variety. And so one of my objectives was, if I have this scaffolding, this material that students can use actively in the class, in the lab, then the difference in levels won't matter because they will just go at their own pace, and I will simply go desk to desk, helping them through, and they will reach whatever level they can reach after 2 intense days. And at the end of those 2 days, of the 20 students, about 4 or 5 had actually completed the whole assignment, the whole set of 12 lessons. There were about 8 of them that were somewhere between lessons, 7, 8, or 9, in the middle. And of course, a few stragglers that really didn't have any programming experience, and they luckily got through step 5, say. But I thought that was pretty good because a bunch of students actually had written a solution to Navier-Stokes in 2 days. And I don't know if you're aware, but Navier-Stokes is pretty, it's a pretty scary thought for many engineering students that you have to write a Navier-Stokes solver. So that's when I thought, wow, this is actually really cool. I'm onto something here. I've prepared this set of notebooks. I've actually coached a group of students through a process of going through these lessons, and some of them really succeeded, and some other ones really went away with some they could possibly finish on their own time, because now they have this material that they can follow. And after this experience, I didn't want to go back. I'm addicted to this stuff, right? I was tasked to teach an aerodynamics class next at GW. And the aerodynamics class, a classical aerodynamics, and I don't know how many of you have a background in physics, but it's really potential theory. How many of you know what I'm talking about, potential theory, maybe in the context of electricity? Okay, quite a few of you. Potential theory, if you go back, I think the classic book on potential theory was written in like 1920 or something. Kellogg is a classic book. And a potential flow or aerodynamics course has been taught in either aeronautics or mechanical engineering context since the early times of aeronautics, and probably in the 50s or 60s, the same time as it is today. It's all theoretical, it's on the blackboard, and it's potential flow solutions and a lot of algebra, take away homework where you do a lot of algebra, come back, and so on. All chalkboard and pen and paper. And here am I in front of a teaching task that is a purely theoretical course, and I want to do notebooks because I like them so much. So what do? I asked myself, well, what is the one thing that I think students should learn in a modern version of an aerodynamics class? And after reflecting for a while, I decided, well, the one thing I want them to know is how you can build a potential flow numerical solution of flow around an airfoil. And then set myself to follow that same pattern of decomposition, I suppose the process of computational thinking, of taking the problem and dividing it, decomposing into steps, and came up with this. Now it's only 11, unfortunately, because the lesson 0 is just an introduction to Python. I wish I could have come up with 12, but it's only 11 in this case. Steps to a solver of the source vortex panel method is the way that you can solve numerically potential flow around an airfoil. So I prepared this with the help of my PhD student as a set of interactive computational lecture notes, basically. So you had the lecture notes, the equations, the material, and the coding. And there was no lecturing in classroom. The students had to read the material, the theoretical part, and work things out. And I basically checked that they were doing the mathematical derivations, but we didn't do any of that in class. In class, we interacted with the computational part of these notebooks. And so I would be walking desk to desk in the classroom, asking questions, using the computational parts of these notebooks as the medium that allowed me to ask questions and have the students inquire the system of potential flow solutions. Now, one of these lessons, you'll see it there, number 6, right in the middle, is the first time the students see the concept of lift. In potential flow, you start constructing the idea of being able to numerically solve for flow around an airfoil producing lift by adding fundamental solutions of potential flow. So for example, if you have an electricity background, there's a source, it's one fundamental solution, and a sink is another fundamental solution. If you bring them infinitely close together, you have a doublet, that's another fundamental solution. And in this field, if you have a doublet and you add a free stream, you get flow around a cylinder, something like in that picture. If you add a vortex in the middle, you get lift. Okay, that's just hand-waving my way through the whole half of an aerodynamics class. So we have lift on a cylinder, lesson 6, and here's just a screenshot of the lesson, how the beginning of the lesson looks for the students when they encounter it. This is the original version in February 2014. And there's a parameter that's available for the students to play with, which is that little kappa there. Well, no, actually, that's the doublet. But further down, there's another parameter, which is the strength of the vortex. And I asked the students to play with that parameter, and they have the code there available to do that. And, well, let me go back to this one. You see this picture, there's some green dots. Those green dots are called the stagnation points. And if you think about this as a flow going around the cylinder, these are streamlines that go up and around. and these streamlines go under the cylinder, and lift is produced upwards in that direction. It's kind of the idea of the spinning baseball, right? When you have spin, you can create a force opposite the direction of motion. And these two green dots are the stagnation points. So that's the picture of my original presentation of the problem in the notebook. And as the students changed the parameter, that is the strength of the vortex inside the cylinder, one student got a picture like that. He raised his hand and he said, Professor, the stagnation points have disappeared. I said, what do you mean the stagnation points have disappeared? I woke over and I said, oh yeah, if I go back, that's how it looked at first, and that's how it looks afterwards, no stagnation points. I said, well, what value of the vortex strength did you use? Well, I used 10. Suppose I'm reproducing here with some parameters what I may have experienced in the classroom with the student then. I said, oh, well, try a different value. Try something smaller. He tried maybe 7. Well, try smaller. He tried 2. They were back with 2. Suppose we were back to that picture. Okay, try bigger. And then suddenly suppose that he tried 5. And then there's 2 stagnation points are right there, and he tried another value. Like in front of me, he started trying different values, and then suddenly he said, oh, the stagnation points move away from the body. I'm like, yeah, that's what happens. That's exactly what happens. Now think about the way that normally a student is exposed to this idea. The teacher would probably draw a picture on the board where the 2 stagnation points are right underneath the cylinder, and he writes gamma bigger than that. He'll draw another picture where the stagnation points are right, like here in this picture, and the gamma is less than equal to that, and then draw another picture where 1 stagnation is moved away from the body and gamma is less, whatever. And the student will dutifully write the same sketches on their notebooks and write gamma bigger than that, gamma equal to that, and then it's done. And he'll probably never remember again, except before the exam, of course. He'll look at the picture and say, ah, yes, of course, go into the exam, probably be able to reproduce those figures in the exam, and then forget 2 days later. I think I'm very, very convinced that the student that went through that process of actually interacting with the code and seeing that happen in front of him and came to this realization and said to me, this is what happens. I'm pretty sure he's going to remember much better than these other students that just simply take notes from the board. So this is why I think the opportunity of Jupyter Notebooks of giving interactive computing within an environment of content which the most basic thing that we do as teachers is to share new content with our students, has a really big opportunity. This idea of interactivity through computing. And this was my experience, and then I started, of course, going back and trying to read and trying to understand what I have seen. After this course that I taught in spring 2014, I was tasked to teach another course, Numerical Methods for Engineers, and I decided to, again, base it on a set of notebooks and to go a little further, put this all online and invite people from across the world to join us using a MOOC platform and teach it as a MOOC. So I announced this at SciPy at the end of my talk in July last year, and then set about to install a platform to invite students to join us. We used the OpenEdX platform. It's an open source online learning software that was developed by MIT and Harvard and Berkeley, and then Stanford as well contributed code, and it was made open source in July 2013. At the time, though, when I announced this, really no one was using this open source software, and people went about their MOOC business by joining either Coursera or edX, right? That was the trend. That was the way to do it. And I decided, no, I'm just going to do it myself, right? And the code is open source. We'll just download, install it. Of course, it was much harder than that, but we got some help and managed to get it done. Here's a screenshot of our own customized version of the OpenEdX platform that we deployed for this course with just 3 courses. Actually, that's just my courses. The whole platform just had my courses and some, little experiment in doing teaching modules. And that is that is the experience that has motivated me to go back and reflect a little bit more about computational thinking and computational learning. So let me take a detour now, and since at BIDS one of the focus areas is reproducibility, ask you, why do you think we are concerned about reproducibility in computation? What is it that we care about? Why is it that we care about reproducibility in computational science or data science? Because it's science, okay.
Science, you know, this is one of the fundamental tenets that you should be able to reproduce an experiment here and there.
Correct, correct. What do you mean by it's science? So this is a proposal. What do you think? Computer simulations create scientific knowledge. Do you think that's a fair statement? Let me see if you agree. Let's see if this works. Let's see, I'm going to do something. This is, okay. Okay, let me go back. I'm sure most of you are online with a device of some sort. So go to this website, b.socrates.com. Enter room number GWCs, if you have any device, any phone, and you answer true or false. Computer simulations create scientific knowledge. I'm going to go back to there. Let's try it. Let's see what you guys think. Let's get a quick poll. b.socrates.com, enter the room number GWCs, and you should see a true or false question, and the true or false is computer simulations create scientific knowledge. Of course, true means yes, and false means no. Do you get it? Do you see it? Yeah, I use this in classrooms in my class, so that's why this is my little code to enter. This is a cheap, free student response system that allows me to ask questions in class, co-opting devices for my purposes. All right. And the question is, computer simulations create scientific knowledge, yes or no? Let me see. I got a live feed now of 82% say yes. So you agree, many of you, except, well, how many? 80% do not agree of the 15 people in the room. That's fair, there's always dissenters. But this is interesting. Many of you do agree that computer simulations create scientific knowledge. Cool. I'll take a screenshot of that. Oh, some dissenters, more dissenters now. Cool, 25%. All right, still took a screenshot of that. 14 people, some of you left the room. So many of you do agree that computer simulations create scientific knowledge. And so if we're creating knowledge, we're actually developing knowledge together through simulation or data analysis, then it's a form of learning. And this was kind of the process I followed as I came with this idea for the SciPy lecture last year. It's a form of learning. We can use computing to learn. And this was, I thought, what I was seeing in the classroom. Students actually using computing to learn, to discover something. We use it in engineering, in computational science all the time, in research. And so we understand that from the point of view of research. And what I want to propose is that we move that same perspective to teaching and learning, that it's a form of learning. And I found myself reading a lot about learning theory because, of course, if we're talking about a form of learning, then I guess we have to sort of know what learning means. And I found myself going back to some of these learning science publications. And I thought that this idea of computing as a form of learning was aligned, interestingly, aligned with the more modern theory of learning that's called connectivism. And this is the thesis that knowledge is distributed across a network of connections. I'll tell you a bit more about what that means. And therefore, learning consists of the ability to construct and traverse those networks. That's the most modern version of a theory of learning that we have. One of the seminal papers was this Connectivism, a learning theory for the digital age, published in 2005 by George Siemens. Previous learning theories are known as behaviorism, cognitivism, and constructivism. Connectivism comes right after. And the idea of this being a theory for the digital age is that, well, over the last few decades, technology has really rearranged how we live, how we communicate, and how we learn. And everything we do in our daily lives now is through technology. So the idea behind this movement is that learning theories have also to now reflect on how technology is used in this social process of learning. And the previous versions of the previous learning theories of up to constructivism are all view learning as something that happens in the person, just inside a person, right? Something happens in your brain, you learn. And they did not address what occurs outside of the person. The possibility that learning could be stored or manipulated by technology happens outside a person. And so this point of view of a learning theory for the digital age, what it did was extend to how learning can be manipulated by technology, how to include technology in our sense-making of the world, and also even describe how learning happens in organizations, so in communities, beyond the single, the person alone. And this is very interesting, starts getting interesting from the point of view of what we know in open source communities. And the idea of connectivism is that learning actually can reside in non-human appliances, the internet, or our network of people, which involves communities. And these are the basic hard-to-grasp ideas. Stephen Downes is the other connectivist early proposers, together with George Siemens. Knowledge is distributed, and knowledge is created by conversation and interactions. The idea that knowledge can be created and shared by an interconnected community of individuals. The interesting thing about this is that now the role of the learner is to participate in a community. And this is why open education is so important, because to participate, you have to be able to create learning objects, share learning objects, remix, and make derivative works. And from the point of view of open source communities, we can't understand those concepts. The idea that open education has to involve sharing. And in connectivism, the starting point for learning occurs when knowledge is created in this process of learners connecting through a community. So what is this idea of a community? George Siemens defines a community as a clustering of similar areas of interest that allows for interaction, sharing, dialoguing, and thinking together. Now, some of you are coders, right? So does this ring a bell? Community, the idea that we are, interacting, dialoguing, thinking together. This is how we function when we develop projects in a community. And if you think about it, not one person can actually produce any of those large projects in open source communities. We do them together. And this is sort of the digital age version of knowledge creation in community. So in the context of all of this learning theory of connectivism, science is understood as, well, a conversation among scientists, a conversation between the scientist and the experimental apparatus. You interrogate your experiment to get answers to your questions, and the social process of science. So science is a social process, a conversation, a constant stream of conversations whereby you're making sense of things. And science becomes this act of connecting things. That's the whole framework of connectivism. And going back to this experience of using computing in as the process of learning, then my connection here is that computing gives you this ability, computing through something like the Jupyter notebooks, where you can mix all forms of content with the interactive use of computing to interrogate a system. This interactivity is the fundamental aspect of using computing as a conversation with the new content that you're learning. We're used to hearing about computing in the context of skills and capacities, but this is more in the line of thinking about it as a literacy, as a material intelligence, something that makes us more intelligent because we have it. And I'm going to skip a couple of slides in the interest of time and skip to the examples of this that I have, and tell you about a couple of historical examples that explain this or help us understand this idea a little bit better. Here's a very interesting book, Changing Minds, by one of your own, a Berkeley professor, Andrea Di Sessa, and he is of the same school of thinking as Seymour Papert, I would think. And there's this passage in this book that says, computers can be the foundation of a new and dramatically enhanced literacy. Notice he's using the word literacy, not skills or problem solving. And here's a passage. If a true computational literacy comes to exist, it will be infrastructural. Okay, what does that mean, infrastructural? Let me give you a couple of examples. Okay, here is a little picture of the publications of Isaac Newton, where he introduces calculus to the world. I won't get into the arguments of who was the inventor of calculus, or whether it was Leibniz or Newton. Let's just use this for our imagination. What is calculus? Well, calculus is a way of writing down and drawing inferences from various aspects of physical quantities that change in time, rates. That's the basic thing. Newton wanted to reason about the instantaneous properties of motions, and he had no proper representation for it, so he had to invent calculus. Now today, we find this pretty normal, but at the time, he just had no language or representation to develop those theories. The process of calculus becoming infrastructural, as it is now in the universities for all technical and mathematical training, happened 200 years later, in the beginning of the 20th century, when a couple of universities, actually Caltech was one of the universities with the influence of the European-trained professors that came in, decided to introduce calculus across the board to all of the students, and early on, freshman year or something. At the time, that was not the way engineers were trained. After this was somehow be deemed a success, a few other universities started adopting this idea, and nowadays we find it pretty natural that all incoming students learn calculus the first year. It's become infrastructural. And the proposal of Andrea Di Sessa in this book is that the true literacy of computation will happen when it's infrastructural, when actually we can take for granted in later courses, for example, that students have had this training so that we don't need to worry about them using computing for their exploration of physics, biology, or whatever it may be. Okay, so here's another passage that I found really interesting. 2000. We may now have sufficiently learnable and powerful computational inscription systems to have dramatic literacy implications. Now, 15 years later, perhaps the dream of Andrea Di Sessa hasn't yet been realized, but potentially we have an opportunity now with all of the exciting things happening in Jupyter project and similar things. Now, how does this work? How does this, using a tool like that, and I was warned to use the word tool very carefully, but this bridge that takes you to everywhere, not to nowhere, to everywhere. That's the idea of a tool that I'm trying to use. How does it work? Here's another example, also from the book of Andrea Di Sessa. He talks about, in this example, how Galileo developed these theorems of uniform motion. So here are his 6 theorems. And I'm going to read the first 2, okay, and see how many of you have had basic physics. Like almost all of you, okay. Theorem 1. If a moving particle carried uniformly at constant speed traverses 2 distances, then the time intervals required are to each other in the ratio of these distances. Okay, that makes sense. Okay. Theorem 2. If a moving particle traverses 2 distances in equal intervals of time, these distances will bear to each other the same ratio as their speeds. And conversely, if the distances are as the speeds, then the times are equal. Well, yeah, that's starting to read a little bit like same thing. And if you read the rest of the theorems, you'll think that this is a little bit too much ado about nothing here. Why did he have to so painfully describe the motion of particles? We, even today, a 9th grader can probably explain this. And you can't imagine how difficult the proofs were, because each one of these theorems carries a proof, and in 2 pages for each one, painfully draws out the proof. Now what we would do is, well, okay, simple variation of distance equals rate times time. So let's get two particles, 2 distances, 2 rates, and 2 times. Use the subscripts 1 and 2 for each one of those. And if we divide the 2 equations to get started, then we can express theorems 1 through 6 in very simple terms. The first theorem just assumes that R1 equals R2. The 2 distances are equal, and therefore immediately the R terms cancel out, leaving, you can see, theorem 2, they're all very, very easily now described in a way that even any high school student absolutely will be able to follow it. We can't really blame Galileo for such a convoluted presentation of his theorems, because Galileo didn't know algebra. In fact, there's not a single equal sign in all of his writings. So how could he give us the simple version of his theorems? In fact, it was a great feat of his imagination to be able to explain those theorems of motion and prove them mathematically without having any knowledge of algebra. It was Descartes that 50 years later just started getting a little bit of a handle on algebra, and it wasn't until the 20th century before it really became infrastructural to the way we teach and learn. So this is the idea of an inscription system that can make us smarter. Right? We have algebra now, so we really cannot, we don't have to go through pages and pages of explanations to understand the simple theorems of motion of Galileo. And in this sense, when computation becomes infrastructural and easily accessible to all students, then, and you know, the inscription systems that Andrea talks about, this way of representing something, like calculus is a way of representing the motions of it, the instantaneous motions of things that change, the instantaneous quantities. Then is when sort of we become smarter as individuals and also as society. And this is the proposal, I guess, I have for this idea of computable content, the idea that we can use notebooks to embed code and visualization together with explanations and mathematics, to use it in throughout the educational system, even for students that are quite young, as Seymour Papert visualized. The idea that media-rich interactive content can become now material intelligence that will make us smarter. And there are some even publishers that are catching on to this, and I really am very eager, enthusiastic to see how this moves to this potential transformational technology, which is educational content that is interactive, fully interactive, and has a compute engine, ideally with no installation friction in the cloud and in all learning platforms. And I want to leave you with this last a citation of Seymour Papert, 1980, don't forget, 35 years ago. I believe that certain uses of very powerful computational technology and computational ideas can provide children with new possibilities for learning, thinking, and growing emotionally as well as cognitively. And 35 years later, maybe we finally do have that technology, and we just need to sort of agree on deploying, making it infrastructural, and understanding how to manage our communities so that we can actually create more knowledge together. That was my proposal for today.